Welcome to class 21 on topics in power electronics and distributed generation. So far in the classes we have been looking at distribution systems from the point of view of trying to understand what the impact of adding distributed generation system to the existing distribution system is going to be, and we identified many concerns. And we saw when we are having long feeders that you could have possibilities of over voltage, under voltage along the feeder depending on location of the DG, what it is trying to do, etc. You have problems related to fault coordination and protection, especially if there is a significant change in fault current levels now, that is result of adding the DG unit. Also we saw that there is a possibility of unintentional islanding, and there are a variety of concerns if you have a situation of unintentional island. Also the compatibility of the existing distribution system equipment is a issue. We saw that the reclosers, there may be timing issues, when you add the DG unit, when you have sectionalizers, you might think that you are operating without you are interrupting the sectionalizer when there is no current, but the DG may introduce current when it is actually opening. There could be problems with open loop transformer, on load tap changing transformers with their boost open loop boost functionality. When you add a DG unit, we saw there could be problems with series voltage regulators on ring feeders. Also these problems become more of a concern when you have more complicated distribution networks such as ring distribution or secondary network distribution. You might have problems with voltage regulators, network protectors, etc. And the other thing we saw is some of these problems might seem to be insignificant when the scale of DG in the feeder is small. So if it is just a couple of solar inverters sitting on one roof, it might not seem like a big problem, but the problem increases as the penetration of DG increases. So if everyone starts adopting DG technology, or there is a DG of significant rating compared to the rating of the feeder, then the problems increase. Also these are technical concerns. There are non-technical concerns such as who would bear the cost if you need to upgrade some of the existing equipment due to the addition of the DG, then who should bear the cost. Also a distribution system has multiple parties that are operating in such a system. You have the distribution service provider, you have a number of consumers, and if you are using the distribution network to send power out, then there is a question of ownership. Are you making use of something that someone else is owning to actually get benefit? Also there are issues of liability. If you, because of the addition of the DG, causes damage to a neighbor or some other owner in that particular setup, then who bears the liability of potential damage? And so it is important not just to address the technical issues, but also the policy and regulatory framework issues associated with distributed generation. Okay. And there are a variety of people looking at it from these different perspectives. And one thing to keep in mind, it is not that there are only problems, there are advantages. You can see that by adding the DG you can get benefits of power quality. Power quality benefits might be and because it is being you can add DG in a selective manner, you could selectively consider which loads need higher power quality and then have DG at those set of loads alone, rather than having to upgrade to a more complex network such as a ring or a network, which would imply cost to all users on that particular network. So, you can have benefits of higher power quality. We also saw that the feeder losses can come down quite dramatically. So, reduction in transmission and distribution losses. You also saw that by appropriately adding the DG unit, then it is possible to have flatter feeder voltage profile. Plus you have other benefits for example, one might consider that adding renewable energy might be seen as a broader societal benefit, and distributed generation is one possible way in which you could add renewables into a system. Of course, you could have renewables as large centralized units too. Also, if you look at the technical problems that we considered, many of the problems require limiting of fault current contributions from the DG. So, you need DG systems where you can limit the fault current when there exists a fault and not have significant difference in fault current levels when you add the DG unit. Also, we saw that some of the equipment might need to control the power flow at different sections of the feeder in an accurate and fast manner depending on the existing load power flow. So, you need fast power control, and you also need possibility of very rapid switching. So, you need also a large number of switchings are possible, and if you look at all these requirements of limiting fault current level, fast power control, need for rapid switching of the interconnection device, all those imply that you would have increased role of power electronics compared to the existing traditional systems that can be used for interconnection. So, the role of power electronics in distributed generation would be increasing as we proceed in time. Okay. But on the flip side, if you look at say a existing power electronic solution with the existing traditional solution, we know that the cost of the power electronic systems are much higher than the existing traditional systems. For example, to send power out, existing synchronous machine is actually much cheaper than a power converter to at this given power level. Also, if you look at existing circuit breaker, that is much cheaper than a semiconductor based circuit breaker. So, at the power level, if you now introduce power electronics, there is a chance that the cost that you would see is much higher, and you want to make sure that you are doing things that are cost effective, and you want to actually look at how can you verify the economics behind adding the power electronic system, so that you are not going back in terms of say having a overall economic system by adding the power electronic components, and your designs or technological changes are moving in the right direction. So, with that background, we will look at a couple of a few ways in which you could look at cost benefit analysis once you add a DG system. Okay. And some of the things to keep in mind are many of the DG technologies compared to the mature existing power system technologies are relatively new and also evolving quite rapidly. So, also in many distribution that generation or storage type of application, the installation at one location may not be identical to the installation at some other location. You might need some customization depending on where you are actually trying to install the unit. So, you also want to look at what are the existing solutions for a given application and how does the DG system compare with the existing solution. Say for example, you might be thinking about a power quality application and you may want to see whether one particular existing solution may be adding a genset or a traditional UPS. How does a DG type of solution compare with the existing solution? Okay. So, if you also we need to look at it in terms of the significant challenges that exist, especially when you are looking at issues such as say climate change or introduction of renewables into the existing system. A major challenge with respect to renewables or renewable energy is not to actually show a proof of concept prototype that the renewable energy system can work, but to actually to ensure that the cost of the renewable system is below that of say for example coal. Coal is considered extremely generating electricity from coal is considered extremely cheap, and you want to make sure that can you make the renewable system cheaper than coal. If that is the case, then you have a natural winner. Okay. So, looking at it from an economic perspective is pretty critical for engineering such systems. Okay. So, we will look at a few metrics that can be used for DG systems, and there are a few ways, say one particular way in which you might make a decision when you are making a purchase or thinking of installing a DG system is what the cost is. I mean, so if you go to a shop, you can easily check whether you have money in your wallet before you decide on whether to purchase a cup of coffee. So, if the coffee cost is higher than what you have in your wallet, you may have to think I will not make this purchase. So, if you look at look at the initial cost, it is a very short time horizon decision. You are making an instantaneous decision. So, And a typical decision like this would be made routinely when we go and make retail purchases, and you are looking at essentially the cost of the product. You may not look at what might be the time implications of making that purchase. For example, you might have to look at, say, some particular item that you buy, but that might need periodic servicing. But if you are just looking at the initial cost, you are not looking at the time a long time horizon. You are just looking at what the initial cost is before you make the decision. So, and you are just looking at the cost of the product. The next thing that you could do is you might look at something that people routinely calculate is what is the payback period. So, if you are in payback period, you are not looking at instantaneous decision making, but you are spending some money and you are getting benefits of by making that purchase over some particular time frame, and you are looking at in how much time can you actually get the benefit of spending that initial sum of money. Okay. So, again here you are relatively looking at a short time frame, not very long. You are talking of something of the order of maybe an year. And here say someone who is working in a commercial environment, maybe your company is making an investment and you want to make sure whether your investment this year will get a return to you this year itself, or will it be seen as a hit this year and then a return only next year, in which case you might take a short term hit in your market value of your company. So, people might say 1 year, if something is giving me return within a year, then it is definitely worth doing. Okay. Here you are looking at cost of product plus cost of services. Okay. Another way in which you could look at evaluating a system is especially a distributed generation type of system, is that you are actually generating energy, and you could look at the cost of energy. Okay. What would be the rupees per kilowatt hour of electrical energy that is being output by such a system, and this is, people look at COE, cost of energy, and you are looking in this particular case at a very long time frame. So, when you are talking about the longer time frame, you could also look at it from design point of view. You might be talking about decades, and say if you are looking at you know what your existing cost of energy is, and if you are looking at introducing a particular source into the system whose cost is going to be twice the existing cost over the next 1 decade, you know that your costs are going to actually ramp up over the decade. Okay. But if you know that your existing system's cost is also going to ramp up, but the system that you are adding is going to stay flat over a longer time frame, then it means that in the long term what you are adding right now will actually make the cost of energy lower over the longer time frame. So, you could make things like policy decisions, which particular energy portfolio you would like to invest in over the next decade, because many times in a field such as energy, you are looking at systems which have lifetimes of 20, 30, 40 years, etc. if you look at a typical wind turbine, you will design it for a life of at least 20 to 25 years. When you are talking about a nuclear plant, people talk about licensing for 40 years, after which you would need to renew the license if at all. If you are looking at a dam, you may be talking about 50 to 100 years lifetime for a dam. So, you are talking about systems which can actually stretch over a much longer time frame compared to some of the more common electronic items like a cell phone, which might be in fashion for a year or maybe 2 years. Okay. So, you are looking at something which can operate over much longer time frames. So, a cost of energy is actually good from a policymaker's point of view. And you are looking at overall benefits to the society. By looking at what would be appropriate portfolio for the particular variety of energy source that you would like to have in your system, and the objective is to do it in a very cost effective manner, keeping in mind all your commitments, like say you would like your people to be healthy and not be suffering from pollution or some other or displacement, or there may be many requirements when you are actually adding the particular energy source. Another possible way of looking at a metric for evaluating the economic value behind a DG system is sometimes people call it effective initial cost, EIC, or sometimes people in the commercial business side may look at it as a net present value. This is actually, it can be of an intermediate time frame. And it can be depending on what time frame you are looking at, whether it is one product which you might intend to operate for maybe just 5,000 operating hours, or a product which might be working for 5 years or 20 years. So, depending on your product, you can set your particular time frame and decide on what is the net present value of that particular product. And so, it can be of benefit to engineering designers or you can look at, say, you are managing a system and you are looking at whether your what your net present value is to make a decision on whether to take one particular choice or another particular choice. So, if you look at such a scheme, it is actually helpful to make can be used to make technical choices. And it considers you can incorporate in it issues of product plus services. You could also have end of life considerations. So, you might in a system you might look at the construction cost, the commissioning cost, the operating cost, whether you have fuel use or some maintenance cost. You might also incorporate the decommissioning cost say associated with the system. For example, if you have a wind turbine, your decommissioning might not be a cost. You might say the steel in the tower might actually give you something that can be sold or reused, but say if you have electronic items, you might have to dispose it in a safe manner. So, you might have some cost associated with disposal of e-waste, etc. So, you have to look at what is the appropriate cost, or actually it can be a benefit depending on the particular system that you are looking at. So, we will look at example of some of these ways of evaluating. Often you might need a combination of all of this. For example, you might like to know whether your particular product has what its outlook is on the very long term. You might also like to make your design decisions when you are actually designing the product based on another metric, and you may also want to check what your payback period is, because your customer to whom your product is sold might actually calculate the payback based on some other metric. So, you may want to look at all these things simultaneously when you are actually looking at a particular DG technology. So, we will start with one way of looking at it. We will look at the payback period. The initial just looking at the initial cost is trivial, all of us do it routinely. If you look at the payback period, we will look specifically at an application such as power quality, where you may want to make a decision on whether to purchase some equipment to mitigate poor power quality. So, you might be thinking about whether to purchase an UPS or a genset or some particular equipment, and if you look at what is the worst situation of power quality, you might have a situation where there is no electricity available to you at all. You might think of an outage. So, if you look at such a situation, not having electricity in one way, it means that you are not paying for the electricity, but often what you miss in terms of your activity that you can actually accomplish during the duration is has a much higher economic value than the cost of the unserved energy. Okay. So, the cost of poor power quality to a customer or to an end user is actually typically much greater than the cost of the unserved energy which is not used because of the fact that the power quality is poor. Okay. Also, if you look at we will look at this in a situation where you might be in a commercial or an industrial environment, and you might say, for example, if you have an outage, you might have a downtime in your production process, you might have lost work, people sitting around in an idle manner because there is no power that is available, and once the power comes back, you might have to go through a recovery process. There may be damage to equipment because of power quality. For example, if you are operating something like a steel mill, if your hot steel bars just sits at a location when the power goes off, you might actually thermally damage the location where the bar came and sat when the power went away. So, depending on your particular application, you might end up with damaging equipment when there is poor power quality. Also, because of the poor power quality, potential damage, etc., you might now have to stock more spares of equipment, your inventories are larger. So, that is another cost that goes up. You also have issues of your product quality going down because of poor power quality. You might be machining one particular piece, and halfway through the machining the power went away, and the machining smoothness might actually become extremely poor at that point. You may have to scrap it, and or there may be blemish, maybe the blemish may be within acceptable tolerance. So, there is always the issue of having material which is blemished or something which you have to totally scrap, and if you have to scrap something, you have to again start off that process from the very beginning. So, there is a rework cost associated with poor power quality. You could have other potential costs associated with power quality because your power went away. Now, your delivery of, maybe you are having a textile unit, you were expected to ship a batch of clothes on the end of the week. Now, because the power went away, you will have to ship it the next week. So, your delivery schedule is delayed, your customer is unhappy, and so you end up paying a in a wide variety of ways because of because of poor power quality. And the question is what could you do to actually then decide when should I now do something to mitigate this problem of poor power quality. And one way to do it is to look at what your payback period is, and looking at simple payback, you would know how much you are going to cost, how much it is going to cost for purchasing the power quality mitigation equipment. So, you might know the cost of what a UPS is, you might know the cost of a genset, you also know what your installation cost is in a particular site. So, you know the overall total investment that you are making for mitigating your situation of poor power quality. Then on the other side you are looking at what benefits that you get, and you want to look at it on an annualized basis. So, we previously saw that there are a number of costs associated with the power quality, and so you could actually calculate what is the cost of idle labor, cost of recovery, cost of increased inventories, etc. on an annualized basis. So, you can, because you are adding the equipment, now you have this benefit as a benefit by adding this particular equipment. But it is not just benefit, you might have to do servicing of the power quality equipment. If it is a genset, you might have to put fuel, you might need to periodically lubricate it. If it is a UPS, you might have to periodically maybe replace the batteries, you might have to fill in the electrolyte up to the appropriate level. So, there is actually ongoing annual expense too, and you are looking at what is the net annual expense, and then you could very easily calculate what your payback period is. It is the net investment divided by your annual returns. So, multiply by 12 to get it in months. So, if you can actually look at this IEEE standard, which gives you a step by step process of looking at evaluating power systems compatibility with electronic process equipment, which is essentially looking at power quality and its impact on industrial or commercial type of environment. So, we will look at an example in this particular situation. Suppose you have a injection molding plant and you are facing say 10 power outages a year. And you go through the list of costs associated with poor power quality, and you look at cost per event. Is rupees say 2,72,000. Per event. Okay. So, this could include the lost labor, lost production, cost to repair, effect of power quality, other miscellaneous costs, etc. And you have a number such as this, and then you look at the capital cost of the DG. And say that is costing 40 lakhs, and you have the installation cost of rupees 20 lakhs. And your existing O&M operation and maintenance cost is rupees 4 lakhs, and what we would assume is by adding this particular say a genset, you are avoiding all the major outages. And then if you look at what your investment is, $40 lakhs plus 20 lakhs, say and then you are looking at returns. There are 10 events per year, about 2.72 lakhs into 10 per event, and your maintenance annual maintenance costs for 4 lakhs. So, your net annual returns is so if you look at then your payback period, so it is longer than 2 years, then you might say maybe it is not worth adding this particular unit, because it is taking a little bit longer for me to get a payback. So, then you might say instead of say 10 events per year means that you are having one major outage per or less than one major outage per month. Suppose you have another situation where you have say one major outage every other week. So, you are having maybe 26 outages per year. So, and because there are more outages, your O&M cost has gone up to, instead of 4 lakhs, it has gone to 8 lakhs. Then if you look at what your new returns would be 26 into so in this case your payback period is so in this case it is less than a year, and you might say okay, now this is an attractive proposition. So, you can see that in this example it is the same equipment that you are trying to sell, you are not selling a different equipment, but it is that your customer requirement is what is changed. So, if you have a product which meets your particular customer requirement, you could actually find it to be a more effective product, whereas if you are designing an equipment which does not match the real power quality requirement that is typical in your particular system, you might find that it is not actually a effective solution. So it is important to understand what your customer requirement is when you are thinking of whether a DG system is going to be effective. Okay. So this is a fairly simple exercise to carry out. Next we will look at the cost of energy exercise, where you are looking at longer term costs and trends in terms of how to actually evaluate whether a DG system may be cost effective or not. Okay. So when you are looking at cost of energy, you are not thinking about capital cost as something that you pay on an instantaneous basis. One assumption that you are making is that the capital cost is actually taken as some sort of a loan, and you are paying an effective equivalent yearly interest back to your lender. So your capital cost is not seen as something that is affecting your system on an instantaneous basis, but spread over the duration, longer time frame over which you are actually operating your equipment. Also you have the operation and maintenance cost, as we discussed in the previous example. Suppose your DG system is making use of some fuel, then depending on the amount of fuel that you put in is the energy that you could produce. So you will have to look at potentially fuel costs. You might also have secondary benefits. For example, you might have a system where, because you are actually producing electricity, you might also have, say, your particular unit doing cogeneration, which means that you might also have say hot water or cold cooling that is being provided. So because of the hot water or cooling, you might actually be able to reduce some other cost, and you might also include that to actually see whether what your benefits are, and you can calculate your cost of energy on an appropriate basis. As you add all these together to form your annual cost, and then you look at what is the energy produced on an annual basis by your DG unit. So you divide the annual cost by the annual energy production, that gives you your cost of energy. So if you look at the cost of energy, if you have something which has higher capital cost, then your cost of energy tends to go up. Okay. If you have something which, say, you have one equipment which will produce energy with some degree of efficiency, and then you have another equipment which produces with a higher degree of efficiency, then typically you will have to pay more for something which is more efficient. Okay. So you might end up paying more for a equipment which is more efficient, but you need to see, are you proportionally getting so much more energy? If you are not, then you might be actually paying more for a equipment than what its energy production justifies. So you will have to look at it in multiple ways to see whether something is acceptable from your cost of energy perspective. Also, if your interest rate is higher, your cost of energy is going to go up. So for example, in an area like renewables or alternate energy, where you might have lots of small companies manufacturing DG units or different dealing with different technologies, the interest rate that a bank charges for a smaller company might be higher than an interest rate that a lender would charge for a larger corporation or for a country for building a larger system. So the smaller startups might feel a tougher time to enter into the business, but once you are successful, things take off, then your interest rate might come down. You might actually accelerate up and be able to ramp up in terms of what you could do. If you look at the fuel cost, it depends on the particular type of technology that you are dealing with. For example, if you are looking at solar energy, wind energy, the renewables, the fuel cost is 0, in which case the actual main cost would be your capital cost. Whereas, if you are looking at something like a fuel based system, then like a diesel genset, we will see that, we will look at an example, we will see that fuel cost is actually a major cost. Okay. If you look at the lifetime over which you are doing these calculations, it is over the lifetime of this equipment. So, you might be talking about 20 to 30 years. And if you look at your operation and maintenance cost, there are two issues associated with operation and maintenance cost. If your equipment is less reliable, you would have higher operation and maintenance cost. Also, if your equipment is less reliable, it means that you would have more time when it is sitting around idle and not producing energy. So, in the numerator the cost would go up, and in the denominator your energy production would come down. So, it is important to have a reliable equipment which would work over the time frame, so as to minimize your cost of energy. So, looking at from all these perspective is an important aspect of looking at a energy system. Okay. So, we will look at an example where you are using, say you are considering a diesel genset, and you want to see, instead of purchasing power from your local distribution company, would it make sense to just run the genset all the time and make use of the energy that is output of from the genset. So, we will look at a simplified problem where if you then look at what is the energy content in 1 liter of diesel fuel, you have 34 megajoules. Okay, no, this is not millijoules, this is megajoules of energy per liter. And so, if you look at the cost, I mean the cost might go up, more often than not it goes up rather than down. And if you look at the cost of electricity, your cost of electricity might range from 4 rupees to 7 rupees depending on what your consumption slab might be. You might be a small consumer, in which case you might have a discount. If you are a large consumer, here we are considering individual consumption, your commercial rates might be even higher. So, we will consider electricity cost from your grid to be 7 rupees per kilowatt hour, and we will assume that the energy conversion from the chemical form in diesel to electricity occurs with the efficiency of 35%. Okay. So, if you look at say 1 liter of fuel N, you are talking about 34 megajoules. So, if you look at it in terms of kilowatt hours, 1 kilowatt hour is 10 to the power of 3 into 1 hour, 3600 seconds. So, this would give you 9.4 kilowatt hours per liter of diesel fuel. Okay. So, if you look at say 1 liter of diesel fuel, your 34 megajoules is equivalent to 9.4 kilowatt hours of energy input. And if you look at for 1 kilowatt hour out with a efficiency of 33% for 1 liter of fuel, you have 35% into 9.4. So, you are talking about 3.3 kilowatt hours of output for 1 liter of fuel. So, if your amount of, so there is a fair amount of waste going out as heat and a small amount as sound going out of your genset, and you can calculate your cost of energy, assuming that say it is running with 1 liter being fed in on a per hour basis. Your cost of energy is 50 rupees per liter, and there are 8760 hours per year. So, the annual energy the annual cost of fuel is 50 rupees into 8760. This is 24 into 24 hours per day, 365 days a year. And if you look at your energy output, this is 3.3 kilowatt hours into 8760 hours per year. So, these two cancel out. So, you get cost of energy about rupees 15 per unit, and 15 is much larger than 7. So, it just does not make sense to run your genset on a continuous basis. You are better off by taking the energy from your distribution supply. Okay. So, then we will look at a second possibility where you might consider your energy, which is now being converted to electricity through one possible path, and then you could also consider that out of the waste heat that is being produced in this particular IC engine. So, fuel to electricity, you have a IC engine plus a synchronous machine plus governor and exciter, all the controls. You might have a heat exchanger which is exchanging the heat and generating thermal output, and your thermal output goes through a second path, and you are able to make use of say 45% of your thermal of your fuel input as thermal output, and you still have an overall waste of 20% of your input energy. So, we will look at, in this particular case, we will assume that because you are now making use of your thermal output, previously maybe you are making use of the thermal output to heat water, maybe in an electric geyser. Now, because you are able to use the thermal output from your DG system, you are saving the energy which would have been spent otherwise in as your energy in your geyser. So, we could think about that as a potential secondary benefit. So, if you look at now your input energy, you have your input energy is the same 9.4 kilowatt hours, and if you look at your electricity output, it is 3.3 kilowatt hours per liter, and your thermal output is now 4.3 kilowatt hours. And then if you look at your cost of energy, so you have your fuel cost which is 50 rupees per liter, and the benefits that you are getting by making use of this as your to prevent your electricity consumption at an alternate point, you would have 4.3 kilowatt hours into 7 rupees per unit which you are saving, divided by your energy production is 3.3 kilowatt hours. So, you now get a number of 6.1 kilowatt hours per unit, and now you have a number which is less than 7. So, potentially now you have something which might be economically feasible compared to the previous situation. So, people do combined heat and power operation of systems to make use of the waste heat to actually provide auxiliary services. Of course, in this case we neglected the capital cost and the maintenance cost, and those costs will actually increase the number of from 6.1. In the next class, what we will do is we will look at, we will assume some cost for the DG system, we will assume some cost for the generator, we will assume some interest rate and operation and maintenance cost, and we will look at how that would then change from the 6.1 and see whether it would still be a cost effective way of generating the generating power in the next class. Thank you.